Dear students, Stereochemistry Part 4 lecture will discuss about the optical isomerism. Optical isomerism, as we discussed in the previous classes, comes under stereoisomerism. So in this lecture, we will see what is optical isomerism. Optical isomerism deals with the plane polarized light. So we will see what is plane polarized light. So generally, a light wave, the wave vibrates in all directions perpendicular to the propagation of the wave. So here you can see that a light wave, when it travels, its vibration will be in all directions perpendicular to the propagation of the wave. So if you take a monochromatic radiation, so monochromatic radiation means the radiation which contain only one wavelength. So it's a single wavelength radiation. So the waves are vibrating in all directions, and when this monochromatic wave is passed through a special kind of prism called nickel prism, which is made up of highly crystalline calcium carbonate. So when this monochromatic wave passes through this nickel prism, the wave comes out of the prism. The vibrations will be restricted to only in one plane, only in one direction. All other waves are blocked by this prism. So this radiation is called this light is called the plane polarized light. So this plane polarized light, when that light passes through an optically active solution, its plane may either get rotated to the right or rotated to the left. So this property is called optical isomerism. Okay. Now, the kind of rotation, how much it will rotate to the right or how much it will rotate to the left, that depends on the wavelength of the radiation and also concentration of the isomer. So it's very difficult to compare the degree of rotation, so that there is a term called specific rotation. So specific rotation is the observed rotation in degrees when plane polarized light is passed through 1 decimeter, that means 10 centimeter of the solution of a substance having a concentration of 1 gram per ml at a specified temperature and for a specified wavelength of the light used. So specific rotation has the same value for a same isomer or same substance, because whatever the observed rotation, you can convert that into specific rotation if you divide the observed rotation by the length in decimeter and also the concentration in gram per ml. So if you divide what the observed rotation with these, then you will get a specific rotation, provided this experiment should be conducted for a particular wavelength of light and at a particular temperature. So the specific rotation may change if you change the wavelength of the radiation as well as if you change the temperature. Okay, so specific rotation means that is same for a substance if you conduct the experiment everywhere. Okay, for example, a representation like this, alpha d 298 equal to plus 66.5 degree for aqueous sucrose solution means, this specification means this optical rotation, it is determined at 298 Kelvin using D-line sodium light. Okay, so here the plus sign, or you can also represent small letter d, is for dextrorotatory. So dextrorotatory means the plane of the plane polarized light is rotated towards right. right hand side of the observer. And minus sign or small letter L, that is for levorotatory. So that means the plane of the plane polarized light is rotated to left. So there are, if one optical isomer rotates the plane of the plane polarized light towards right, then its other isomer will rotate it into the left to the same extent if we express the rotation in specific rotation. Okay, so what is optical isomerism? So optical isomerism is a type of stereoisomerism in which the isomers resemble in most of their properties but differ in their behavior towards plane polarized light. So you should understand what is plane polarized light. Then the isomers, they differ only in the behavior towards the plane polarized light. One isomer will rotate the plane of the plane polarized light to right, whereas the other isomer of the same substance, that will rotate to the left. Okay, so that is optical isomerism. Now, what is the reason for optical isomerism, or which molecules show optical isomerism? That is the point of discussion. Next. So the condition for a molecule to show optical isomerism is chirality or dissymmetry. So what is chirality or dissymmetry? It is nothing but the non-superimposability of a structure on its mirror image. So that is chirality or dissymmetry. So that is non-superimposability of a structure on its mirror image. So we will see what is that. And this chirality or dissymmetry, that is the necessary condition for a molecule to show optical isomerism. So those molecules which are chiral or dissymmetric, those molecules will show optical isomerism. Okay, so let's examine these pictures. Okay, here I have shown the mirror image of your hand. So for example, your right hand is the mirror image of your left hand. Okay, but they are non-superimposable mirror image. That means you cannot superimpose this hand with this one, because if you try to superimpose this one with this one, what will happen is your thumb will go to the small finger of here, and your small finger will go to here as well. So the fingers won't match. So this mirror image you cannot superimpose with this one. So this is what we call the non-superimposable mirror image. Whereas if you take this example, it's an alphabet A, and this is the mirror image of A. So you can superimpose this mirror image with the object. So this is a superimposable mirror image. Okay, so if a molecule, its structure is non-superimposable to its mirror image, that molecule is chiral, or that molecule has chirality, or that molecule is dissymmetric, and that molecule will show optical isomerism. We will see detail. So a chiral molecule or dissymmetric molecule, that molecule do not possess a plane of symmetry. So that is one of the aspects of a chiral molecule or dissymmetric molecule, that do not possess a plane of symmetry. So let's see what is plane of symmetry. So there are different kinds of symmetry elements. So symmetry elements means if you examine a molecule and if you do some symmetry operations, you will know that whether that molecule has that symmetry. For example, plane of symmetry or mirror plane is an imaginary plane that divides a molecule into two halves such that one is the exact mirror image of the other. So if you consider an imaginary plane, mirror plane, which bisects through the molecule, and if one half is the mirror image of the other, then we say that that molecule has what symmetry? Plane of symmetry. So the other kinds of symmetry elements are axis of symmetry, that is based on rotation, alternate axis of symmetry, that is based on rotation and reflection, and center of symmetry. So you don't have to worry about this because this is out of scope of our current discussion. But you should know what is a plane of symmetry. Why? Because if any molecule do not possess a plane of symmetry, that molecule is chiral or disymmetric. So if a molecule is chiral or disymmetric, that will show optical isomerism. So that means the absence of plane of symmetry in a molecule makes it chiral or disymmetric. That will help the molecule to exhibit optical isomerism. Okay. So there is another term which is asymmetric molecule. So we know what is disymmetric molecule. Disymmetric molecule means that molecule does not possess a plane of symmetry. So asymmetric molecule means if a molecule does not possess any of these symmetry elements, then that molecule is known as asymmetric molecule. So that means all asymmetric molecules are disymmetric. Obviously, because asymmetric molecule means none of the symmetry elements present. So that means that molecule does not possess a plane of symmetry as well. So all asymmetric molecules are disymmetric. But all disymmetric molecules need not be asymmetric, because if a molecule does not possess plane of symmetry, then that doesn't mean that that molecule doesn't have other kind of symmetry elements. Okay, so all asymmetric molecules are disymmetric, but all disymmetric molecules need not be asymmetric. However, the necessary condition for a molecule to show optical isomerism is dissymmetry or chirality. That means the molecule should not possess a plane of symmetry. Okay, now a molecule has to be chiral or disymmetric. One of the conditions is presence of a chiral center or stereogenic center or chiral carbon. So let's see what is a chiral carbon. You know that carbon has a valency of 4. If 4 valencies of a carbon atom are satisfied by different atoms or different groups, then that carbon atom is called chiral carbon or asymmetric carbon. Okay. So presence of such carbon atom or atoms, more than one chiral atom, carbon atoms, that may make or that can render chirality or dissymmetry to the molecule. So a compound where there is a chiral carbon. Chiral carbon means all of its 4 valencies are satisfied by different groups or atoms. So if a molecule possesses a chiral carbon, that molecule exhibit optical isomerism because that molecule is then disymmetric. Okay. So consider a molecule like this. Here, this gray colored ball, that is the carbon atom, and I have shown other 4 atoms or groups attached to this carbon atom, and definitely this is in tetrahedral shape because if all 4 valencies are satisfied by different groups, definitely that carbon atom is in sp3 hybridization. So this is red one atom or one group, green one, different atom, yellow, third one, and blue, fourth one. Okay, so now this carbon atom has 4 valencies satisfied by different groups or atoms. And if I keep a mirror plane, and if I take the reflection of this molecule, it will be like this. And you can see that if you try to superimpose this mirror image with this one, you cannot do that. So if you take this one and try to place it here, the red ball will match to red ball. Okay, the yellow ball will match to the yellow ball. No problem. But in the position of blue ball, here comes the green one, and in the position of green ball, here comes the blue one. So that means you cannot superimpose this mirror image with this one. Even if you try to rotate this one, then still you cannot superimpose this one with this one. So that means these two are isomers, means these two are not same molecule, they are different, but they are isomers. Okay, so these two molecules are non-superimposable mirror images. That means this molecule does not possess a plane of symmetry, or these molecules are dissymmetric. So why these molecules are dissymmetric? Because it has a chiral carbon. So what is a chiral carbon? A carbon whose 4 valencies are satisfied by different groups or different atoms. Okay. So presence of a chiral carbon or chiral center or stereogenic center is one of the reasons for optical isomerism. There are some other reasons as well, which we are not going to discuss here. Okay. Now,